Welcome back to the drawing board, and today we'll be talking about the design of walers and the combined effects that act upon them. When I say combined effects, I'm talking about axial force, bending moment and shear forces all acting on the waler at the same time. I won't be talking about torsion because you don't usually see torsional effects on the kind of walers that we do. I'm going to start by mentioning the cauchy stress tensor. You don't have to understand all of it, but it's just a way of expressing the state of stress at any point in the material by combining this 9-part matrix, which includes any forces in any direction acting on any plane. These three guys down the middle are the direct stresses, so the compression in each direction. And these here, you can pair them up. These are the stresses going around in each plane. And having a look at this little diagram here, the stresses going around anti-clockwise will have to be equalled by the stresses going clockwise in order to maintain balance. So these two, and these two can be paired up, and it makes writing this next equation quite a lot simpler. Von Mises' yield criterion is basically the stress that you get here, and it has to be less than the yield strength of the material. If it isn't, then your material begins to yield plastically. If it is, then your material will stay put, and that's fine. So writing out this equation, you have subtractions of the main stresses, all squared, and then you have lots of your shear stresses, and that's all divided by 2. So I was talking about subtracting the principal stresses, and I missed one of the most interesting facts about von Mises' criterion. If you had equal stresses in all principal planes, it would be almost the same as having no stresses at all. If you squashed something from, say, 2 directions, the only place it could deform is by squidging out up and down. But if you're also applying the stress there, it can't move anywhere, and there can be no yield if there is no deformation. So what's quite interesting is if you actually apply an equal force to one plane and an equal force to the other, it's almost the same as having this scenario, but with these forces taken away, which basically equates to a tension force equal to a single one of these principal stresses. Not very useful, but very interesting. I'm not going to go into it too deeply, but what you can actually get is if you read the Eurocode, there's a very similar equation. It's the very first equation that you have at the start of the Eurocode section 6 in Eurocode 3. Instead of doing the square of all of these different stresses, it takes the utilisation in each of these stress directions, and then it compares that, and as long as that utilisation overall is less than 1, then you haven't overutilised your steel. One really important thing to mention is that if you come out of this equation and you have utilisation of 0.81, that's not 81%, it's 90%, because although the square root of 1 is 1, you still have to square root, because that's a square there. So if you have 50% coming out of here, or 0.5, you've actually 70% utilised. So if you did get the answer of 0.5, don't think to yourself, oh, I can double the load on that. You couldn't, you could only add an extra 30%. Why then are there all these extra rules in Eurocode 3? Because the von Mises yield criterion would make you think that if I got a point of stress that was bigger than my yield stress, that my thing would start bending. Well, that's assuming an elastic distribution, and if you're dealing with a class 3 or a class 4 section, that would certainly be true. But most of what we deal with in steel, certainly most of the UKB and UKC sections, class 1 or class 2, and you can use plastic redistribution of stresses. And this doesn't just apply in redistributing moments along the length of a beam, this also applies within the structure of the beam itself. So if you look carefully at them, the axial load, this will be usually uniformly distributed throughout the depth of the section. Bending moments, bigger at the sides if you're talking elastic, and then not so much in the middle. And shear forces, generally speaking, high in the middle and not so much at the side. So it gives you these extra rules so that you can redistribute and move around the stresses and get every single part of your beam being well utilised, rather than just overutilising one part of it. So taking a bit of a closer look, if your shear force is less than half of the shear resistance, then you don't even have to worry about it, because this amount used here isn't significant enough that it would affect these two. If it is, it's not a linear relationship. It's not like if I've used 80% of my shear, I've only got 20% of the strength of my beam left. You get to use this nifty little rule here, which gives you this rho factor. You reduce the effective yield strength of the material based on how much of the shear strength you've utilised. You can ignore axial stress as well if that's not very high. Again, the reason being that if you've only used a quarter of the strength of the material, well, think about triangles only taking up half of the area. It's that similar principle, is that if you've only used a little bit of this, you could easily knock off the end of that triangle and redistribute some of that force and some of that stress into this web here. And if you do have an axial force that's greater, then you reduce the bending moment. And this equation is different for every single beam. For I sections, they all follow a ratio of how much of your bending force compared to your bending resistance, and a ratio of how much web you've got to how much flange, or in the case of a square hollow section, for instance, how much you've got on the top and bottom compared to the two sides if it was a square hollow section. But for the case of the I sections, the UCs and the UBs, you take a ratio of force to resistance, you take a ratio of how much web to flange, and you plug those into the equations from Eurocode, and it gives you a slight reduction. Just because you've used half of your axial strength doesn't mean you're going to have to reduce your bending resistance by half again. It lets you move things around and gives you a less conservative but much more economical strength out of your beam. I haven't covered everything, but hopefully that gives you a little bit of instruction in the combined effects to Eurocode 3. Thank you very much.